Hey, we're still talking about the gradient as part of vector calculus, differential vector calculus, and we're on to the second interpretation of the gradient. The first was the direction of steepest ascent. Now we're going to talk about its interpretation as direction normal to a curve or a surface. The first thing we need to talk about a little bit ahead of time is this idea of a level curve or level surface. Let's say, so I can draw it, I have a function of just two variables, x and y. So for each point in the xy plane, I get a value of the function, and all those values constitute some kind of surface. If I freeze the value of that function, meaning I take some constant here and set this function equal to that constant, it's like taking a slice through that surface. So here, down here in the xy plane would be a level curve associated with this surface. If I took a few different cuts, I would get multiple level curves, and it would start looking like a contour map of a hill. It would be a contour map of this surface hill. So usually one of the first things we need to do, a lot of times if you just have a function of x and y, so y is some function of x, we make a level curve out of it by just getting all the variables on one side. So here was a function we will use. We'll just subtract the right side from the left. So here now is a function. If I set it equal to something, I would get a curve. If I had three variables and I had, for example, you were given a z, some function of x and y, you would form this level function by subtracting the right side from the left side again. If I set this equal to something, I would get a level surface. Well, here, when I only had two variables, I got a level curve. But if there's three variables, you get a level surface. Here's a couple of examples. Somebody gives you z equals x squared plus y squared. Here's the function you make out. There's the function we need. Once you set it to a constant or whatever, that's when you get surface or the curve. Anyway, so what does it mean to be normal or perpendicular to a curve or a surface? Well, if it's just a curve, you see a curve in two dimensions, it would have a tangent line, right? At a given point along that curve, it has a tangent line. So perpendicular to that tangent line is what we call normal or perpendicular. What about if it's a surface? It's a little bit more complicated definition. Say I have this surface here. There should be a z up here. Now my variables are x, y, and z. This is not the value of the function. This is the p component. But this is a surface in three dimensions. Take some point on that surface. Every curve in that surface that goes through that point has a tangent line there, right? All the tangent lines combined would be in this tangent plane. And the normal vector is perpendicular to that tangent plane. It's also perpendicular to all those curves tangent lines. So here you see what a tangent plane means and what the normal vector means at a point on a surface. It turns out the gradient of f is the direction of that normal. What does that mean, or what's an interpretation of that? Let's go back to where you have a function that's just a function of the two variables x and y. This is not a level curve or surface. This is the function or the surface formed by the function. A level curve is when I take a slice through it. If I took many slices, I get this contour map. Every time the gradient at a given point is in a direction that's perpendicular to those level curves. So it's the gradient not only points in the direction where you go up this function most rapidly, it also crosses a level curve for that function perpendicularly. The first time you go through this takes a little bit of thinking. These are two different pictures of two different things. In this case, this third dimension is the function itself. And the gradient was the direction in which that surface goes up the fastest at a given point. Here, the third dimension is the third variable, third coordinate, x, y, and z. The function in this case would be in the fourth dimension, and I can't draw it. If you set that function equal to a constant, then you get this surface in x, y, and z space. And there the interpretation of the gradient is this normal direction. It might take a while to sink in. Two interpretations of the gradient. Two different pictures of two different things. You have to come back to this if you don't understand this. First time I went through this or learned it, it took me a couple days, if not more, to see. So here's a problem that uses some of those concepts. Find the points on the surface. The surface is given to you, which the gradient is parallel to a given vector. Well, what are some of the concepts? Parallel means that some scalar multiple of that vector. Gradient, well, what's the gradient of the surface? First, we have to form the level surface equivalent function. So we'll just subtract the right side from the left. Here's our function. We take its gradient. We get minus 2x minus 2y 1. That gradient is parallel to this guy, which means it's a scalar multiple. Let's call that C. Something I have to determine. So this has to be true. This one equation, one vector equation, is actually three scalar equations. How many variables? X, Y, Z, and C. Three equations, four unknowns. What's the fourth equation? It says find the points on the surface. So the points also have to satisfy this equation. This gives me three equations. Minus 2x equals 4c. Minus 2y equals c. And 1 equals a half c. Taking that third equation, I get what c is. That lets me put what x and y are, all from here. What is z? I go back to this equation. E equals at x squared plus y squared, I get 17. Here we go. Here's the answer. All right, here's another problem. Find the equation of a tangent plane to the graph of this equation that's indicated. Means find, well, first you got to find the normal curve, which is the gradient. Find the gradient of this surface. First, we set this up in level curves, level surface format. Subtract the right side from the left. Here's our function. Take its gradient. That'll be minus 1 over this times the derivative of this, which here's the partial with respect to x. Here's the partial with respect to y, and with respect to z. gradient. At this point, plug in that for x, that for y, and 0 for z. I get this vector. So this is the normal vector. Write an equation of the tangent plane. Well, I have a normal vector and I have a point. Now we go back to the previous module, how to write the equation of a plane. Remember, it had a certain format. X minus the x coordinate, y minus the y coordinate, z minus the z coordinate. Each multiplied by the components of that normal vector. X goes up here, the y. Here's the equation of the plane. And we simplify this. Third example, find all points on the surface which the tangent plane is parallel to another plane. Go through the thinking on this. Two planes are parallel if their normal vectors are parallel. Remember that little fact. And you can find the normal vector from the equation of a plane, and it's like this. It's just 2, 4, 6. This guy's normal vector is 2, 4, 6. This guy's normal vector, you got to take the gradient. Gradient is going to be 2x, 2y, 2z. It's parallel to this guy's normal vector. Scalar multiple of 2, 4, 6. This is like the problem we just did. First problem. We have 3 scalar equations coming out of this, 4 unknowns, and it says find all points on this surface. This would be our fourth equation. This says 2x equals 2c, 2y equals 4c, 2z equals 6c. I have these. Once I have c, I have x, y, and z. All points on the surface, which means this also has to be satisfied. X equals c, so I have c squared plus 4c squared plus 9c squared. 14c squared, and that has to equal 7, which means c squared equals 2. This. I have 2 possibilities for c, so I have 2 points. It asks for all points, not just any point. Here are the 2 possible points at which the tangent plane is. The third interpretation is going to be vector fields, and we'll save that for another video.